vocabulary for our triangles. A midsegment. A midsegment, it's a segment that connects the blank of two sides of a triangle. These are midpoints. So a midsegment, and you have to draw a little picture here. So if I have a triangle, if you find the midpoint of two sides and you connect them, that's a midsegment. So you look for, this is a midpoint, this is a midpoint. If you connect them, you have something called a midsegment. A perpendicular bisector. It's a segment, ray line, something that is perpendicular to a segment at its midpoint. So here's my triangle. It's a line or a segment. It's perpendicular and it bisects it. Now if you extend this, it may or may not hit that vertex. It may not. Let's see if I can help you. So maybe it's over here. So it doesn't necessarily hit the vertex on the other side. That's a perpendicular bisector. What else do we have? We have angle bisectors. We know what an angle bisector is, right? A segment, ray, or line or plane that divides an angle into two angles that are, you should know this one, congruent, right? So if you have an angle bisector in a triangle, it's over here and it makes two congruent angles. That's what an angle bisector does. Okay. What else we got here? Median. A median. It's a segment from a vertex to something of the opposite side. So I'm going to draw it over here. I've got a little more room here. A median. So you start from a vertex and you're going to go to the midpoint. So that's congruent, that's congruent. Don't confuse that with a midsegment. How is this different from a midsegment? What's the midsegment? How is it different from a midsegment? Yeah, see, a midsegment might be like across here, because it's connecting two sides. This one starts at a vertex and goes to a midpoint. Altitude. Altitude. What? Segment to midpoint. Midpoint. Right? We're going to the midpoint. And altitude. Now I think of this one to me I can make perfect sense out of. Because in altitude, like if you're an airplane at altitude, and let's pretend you're just hovering for a minute, you drop something, what kind of line do you get to the ground? Right? It's going to be a perpendicular line. If you drop something out of an airplane, so in altitude, it's a perpendicular, what's what I got here? A perpendicular segment from a vertex to the opposite side. Perpendicular segment. So an example here, I'll get rid of my little airplane drop, is if you have a triangle, you drop a perpendicular. This is the height of a triangle, and altitude is the height of a triangle. Do not necessarily think that these two pieces are congruent. It does not have to be a bisector. Sometimes it is, but it does not have to be a bisector here. It's just a perpendicular line. The height gives you the height of a triangle. Equidistant, these are just some words here. A point is equidistant from two figures if the point is the same distance from each figure. So when I use that word equidistant, equal distance, it's kind of in the name. There's an equal distance, same distance. A point of concurrency is a fancy name for where a bunch of lines or segments meet up. A point where lines in a triangle, such as medians, altitudes, and bisectors, where they intersect. And a point of concurrency is thought to be like a center. It's kind of another way of thinking about a center of a triangle. And a triangle can have many centers, different ways of defining it. So points of concurrency, if I were to connect all my midsegments, this one to that one, that one to that one, that's a bad example, let's do angle bisectors. If I make all the angle bisectors, this would be a point of concurrency. It's the center of the triangle based on angle bisectors. So we're going to look at all of these in more detail. So let's start with midsegments. A midsegment is a segment that connects the midpoints of two sides of a triangle. So here's my big picture. The theorem. The segment connecting the midpoints of two sides of a triangle is parallel to the third side and half as long. So this one's twice as long. Or if you know this length, this one's half the length. And they're also parallel. Those are parallel markers right there. That's my theorem with midsegments. So the midsegment is parallel to the side of the triangle that it does not intersect. Meaning this guy, the one it looks parallel to. The midsegment is half the length of the other side. Every triangle has exactly 3, because I connect this midsegment with this guy's midsegment, and I can connect those midsegments as well. The 3 midsegments create 4 congruent triangles. Look at that. This one is congruent to that one, is congruent to that one, is congruent to that one. Really? Well, let's see. Look at this guy here. He's half of that one, right? Well, what's half of that one? That's like my 3 marks. Do we agree? Is this one congruent to that one? It's congruent to that one. Because it's half the side. How about this guy here? He's going to get 1 mark. How come? Because he's half of that side. How about this guy? He gets 2 marks. Now look at all the triangles. And we have a lot of sides going on. Just kind of cool. You get 4 congruent little triangles in there. Neat. Yes. So what are some examples of what you do with this, or how you might be asked about them? So if they tell you ST and TU are midsegments, find the length of PR, which is this one, and the length of TU, which is that one. Let's start with the length of PR. I'm looking for this guy. This is a midsegment, right? And it's 8 feet. So what's PR? Yeah, 16. Because it's half the length of the parallel side. How about now this guy? Here's TU, and here's QP. This is a midsegment. QP is 10 feet. So what's this one going to be? 5 feet. Yes, you're right. I should use my units. You're right. See how that works? Just take a nap. Let's look at this guy here. XC and DY are midsegments. Find MN. That's this guy. And why? Oh my God, that's this one. Well, can we look around here? Can I find his matching midsegment? That's here. And it says his midsegment is 26.5 centimeters. That's XZ. So what's MN going to be? We're just doing the math here, and that's what's taking so long. Well, I have to double this, right? 26.5 times 2. That's 53 centimeters, so that's MN. And then I want YZ. Let's see, that one's a midsegment. What's going on across the way? That one's 28. So what's YZ going to be? 14. Yes. Let's look at this guy. ED and DF are midsegments. These 2 guys are midsegments. And usually what I do when I hear midsegment is I just start, why not? Who knows? Maybe I need to know that. I mark it. Why not? Can't hurt. Let's see, find DF and DC. So here's DF. What's DF going to be? DF right here. It's a midsegment, so it's half the length of this side. It's going to be 7. It's not necessarily the length of the other midsegment. Let's see, here is DE. I want to find BC. So what's BC going to be? 12. What if they said find, instead of BC, what if they said find DF? What would BF be? Yeah? Okay. These little pieces are all congruent. So we got that. What's going on here? SB is congruent to SC, and I am marking up my diagram. RS is parallel to AC. And RS, the length of this is half the length of the side opposite it there. Show that R is the midpoint of BA. Alright, how do I do that? How do I do that? And look at the theorem that we just got. See if that helps. Yeah, what do you think, Asa?
Might be compatible, but AC is congruent to BC.
How do I know that?
Like RS.
Okay, ours is parallel. Therefore, and its measure is half of that. Therefore, it must be a midsegment. be a midpoint. So we're kind of, by concluding, because it told us all this stuff here, that means that RS is a midsegment. And if R is a midsegment, that means that these two things are congruent, AR, because it's a midpoint. So here, and is a midpoint, and R is a midpoint. And why is that? Because that's what a midsegment is. It connects the midpoint. So we're kind of going back around the other way, coming with other information. So if you are given parallel, and this is half of that, then you know you have a midsegment. You got it. And you can use all the properties that go with a midsegment. Okay. That's just one thing we have to know about. How about perpendicular bisectors? Let's remind ourselves what that is. It's a segment that is perpendicular to the side of the triangle at its midpoint. This picture is a little complicated. But remember, they don't necessarily hit vertices. Like a line that goes straight, they don't necessarily hit the vertex. All it means is that this is perpendicular and it bisects. This one's perpendicular and it bisects. You basically find, you find the midpoint and then you draw a perpendicular line from it. And certain properties pop out. So here's a theorem and it's converse, so it's a biconditional. In a plane, a point is on the perpendicular bisector of a segment if and only if it is equidistant from the endpoints of the segment. So here's the segment, and here's its perpendicular bisector. So if I connect, make this line long, any points on here, they're equidistant, the same distance from the endpoint. So if I draw like one here, this is also those pieces of congruent. This is kind of an important feature of the perpendicular bisector. Okay, so what else do we know? Okay, so it intersects the side of the triangle at its midpoint. That's what it means to be a bisector. Perpendicular bisector intersects at a right angle because it's perpendicular. Any point on the perpendicular bisector is equidistant from the endpoint of that segment. Every triangle has at least 3. So I can see it. You have 3 sides. So you can make 3 perpendicular bisectors. And look how they're all meeting up. They're all meeting up. This is a point of concurrency. It's a center of a triangle. And it's called a circumcenter. So if you have 3 perpendicular bisectors, they are all going to meet at the same point. We call that point a circumcenter. And it's equidistant from the 3 vertices. So this thing here, if you connect the circumcenter to all the vertices, 3 congruent segments. Wow, that's a lot of things. So let's look at some examples here. So KM is the perpendicular bisector of JL. Right away I got to do this. Perpendicular bisector, I'm also going to put one of these. I don't know if I need it. And you know what else I know? This one to that one, congruent. Why? Because any point on a perpendicular bisector equidistant to the endpoint. Mark that up first thing. Does this become easier once you marked it up? Yeah, I mean, what can I do? I want to find really X and Y so I can find J and Z. Yeah? Because I use the theorem. Here's my segment. Here's my perpendicular bisector. Whoops. Any point on this perpendicular bisector is equidistant, the same distance from the endpoint. And being the same distance means it's congruent. They have the same length. That's what that's why I interpret that theorem. Yeah.
Would you do 7x equals 3x plus 16?
I can totally do that. So I'm going to go ahead and solve that. So x equals 4. So what's this one? 28. Do I need it? I don't know. Yeah, that's got to be 28 too. I always plug them in because I expect them to be the same. If they're not, I made a mistake. What do I know about these two things? They're also going to be congruent because it's a bisector. Bisectors bisect into 2 congruent pieces. So what am I getting? 3y equals 9. So y equals 3. This one's 15. This one should be 15 too. Let's make sure. 6 plus 9. Good. Now find JK. JK is 15. And what's JM? 28. So, fill in reviewing what you know, to find some of these other pieces here. Let's look at another example. DC is the perpendicular bisector of AB, and that's congruent to that. This one's going to be congruent to that one. Let's see, what else do I need to know? And AE is congruent to BE, or give me that. What segment lengths are equal? Well, if you mark the diagram as you go, I can see that BD is going to be equal to AD. I can see also that BC, BC equal to AC, and they're giving me that BE equals AD. I think that's all the congruent segments. That's quite a few. Is point E on DC. Now, if I was to extend this all the way through, are they going to meet up? This point here. Why? Who said yes? Thomas, how come? How come? That's what the theorem says. They're equidistant, so it must be on there, yes. You're absolutely right. Because they're equidistant, then yeah, it must have been on the perpendicular bisector. That's how it works. What about this guy? The circumcenter. So now we have to know that circumcenter now is talking about perpendicular bisectors. Once you hear circumcenter, okay, perpendicular bisector of ABC is point G. Find GB. Okay, well, how am I going to do that? How do I do that?
Aren't all the lengths from the vertices the same line?
This is kind of paying attention. So these are all the same length, right? Can we have that in the other picture? So what's the length of BG? GB? 7. How do I know that? Because this one's 7 right here. So they're all going to be 7. Oh, it turns out that one. As long as you kind of know these little properties. Yeah. Which one? No. BG. I don't know what those are. Those are actually the perpendicular bisector lengths. Those don't have to be congruent. But the vertex to the circumcenter, they're all going to be congruent. You can't make an assumption about these guys. So wow, what about that? Angle bisector. Let's go. We're moving it. A segment where your line that divides an angle into two congruent pieces. Here's the theorem. A point is on the bisector of an angle if and only if. So biconditional. It is in the interior of the angle and it is equidistant from the two sides of the angle. And this means that if that's all true, you have a bisector. So it works the same way. How does that kind of interpret? So you draw an angle, you make it bisector, and then if you take a point on the bisector itself and you drop a horizontal line, because that's how you get distance, they are going to be congruent. No matter where you pick, you're going to have congruence. Okay? So let's see, what do we know here? An angle bisector creates two congruent angles where it intersects the vertex. The distance from a point to the line is the length of the perpendicular segment from the point to the line. Oh, yeah, that's this. I think we're talking about this here. Any point on the angle bisector equal distance from the side. Every triangle has 3 of them. So now if you look at 3 angle bisectors, you're bisecting here, you're bisecting this one, and then you're bisecting that one. They do all meet up. You get a point of concurrency. We get a new kind of center of a triangle. This one's called an incenter. So it's a circumcenter. Well, those are perpendicular bisectors. Angle bisectors have incenters, and it's equidistant from the 3 sides of the triangle if you draw a segment perpendicular. Oh. So yeah, so I guess that means these pieces. As long as they're in some perpendiculars, they're equidistant. But let's look at some examples. Let's do that. Because it gets confusing. All right, find LM. Is this a bisector? How do I know this is an angle bisector? Are these 2 angles congruent? Then I have an angle bisector. So I'm dropping these little perpendiculars here. So what do I know about this? They have to be congruent. So what is LM? 5. That's it. That's it. What about this guy here? For what value of x does P lie on the bisector 8. So for what value of x? Well, what has to be true for this to be on here? I didn't ask what x is. What has to be true? Yeah. Yeah, they have to be congruent because that's what makes it an angle bisector. So I do have to set this guy up there to be congruent. 2x equals 8. X does equal 4. Whoever shouted that out before. But you want more than answers. Like why? In center. So now you read a question like, oh, in center, that goes with angle bisectors. So you kind of have to remember that. So here it is, angle bisectors. Find VS. Where is VS? Oh, it's right here. Okay, VS. Oh, what's that going to be? Well, this one's a little bit trickier. I kind of found here a complete triangle. Because what do I know about these little pieces here? According to that theorem, they have to be congruent, right? So, I just have to find this. And we haven't quite done the Pythagorean theorem formally, but do we remember how it works? I got a 15. So I want to find like that missing side. How do I do that? You don't know. And so let me just see if I can turn it around. 17 squared minus 15 squared. So x is going to be the square root of that thing, right? So I tell you what, I put that in my calculator. Actually, I didn't, but you could. And then what do you get? 8. I believe you get 8. So this one I had to use the Pythagorean theorem. I had to think a little bit. But once I have this side, I know all 3 of these. So what's VS? The length of VS is 8. So sometimes we have to do kind of clever things. Oh, no. Medians. It's a segment from a vertex to the midpoint of the opposite side. So now I'm going from a vertex connecting midpoints. So all those points are midpoints. So let's see. Yep, that's what they are. The median creates 2 congruent segments on the side it intersects because it's a bisector. So that's saying these and these, right, you have some congruence. Every triangle has exactly 3 because you have 3 vertices. And look at that. We do have a point of concurrency. We call that a centroid. They must have been running out of names. So I mean, there's so many, a centroid. We're going to call that for a median where they all meet up. Now here's the fun part. Okay, the distance from a vertex to the centroid is 2/3 of the length of the whole thing. All right, so from here to here, it's 2/3 of this whole thing. So there's one piece missing here. That means this one's 1/3. If you add the 2/3 and the 1/3, you're going to get the entire length. So let's just look at some examples about what we do with that. Okay, I hope I have one of that. Let's just do this one here. In ABC, D is the centroid. So now I have to know what that means. The centroid is like working with medians. So now I know I've got medians. So that's supposed to go. I'm just marking off. Do I need this or not? I don't know yet. But I know they're medians. So I know I've got congruent pieces. It says BD is 12. A little hard to read here. This length. Find DG and BG. The whole thing. Well, 12 is 2/3 of the whole thing, right? Isn't that my theorem? 12 is 2/3 of the whole thing. Yeah. So, how do I solve for BG? You know how you solve an equation like this? Yeah? Multiply by? Right, multiply by that reciprocal, there's my BG. 2, 12, 6, 18. So that's the whole thing is 18. What's the little piece then? Right, this whole thing is 18, so what's the little piece? This one's 12. Whole thing, yeah, what are we going to get? 6. Anybody noticing here, when you know this is 12, this is going to be half of it? Because this is 2/3, right? This is 1/3. So it's actually easier than it sounds. I never go through this whole big story. Don't tell me. I know because this is 2/3 and it's 12, then 1/3 is half of it. And it's a little bit faster. PQR. S is a centroid, so again, that means median. UQ. Oh, shit. This one. Here. 5. outside the line. So if you have a triangle that looks like this, and I want the altitude, the height from this vertex, you have to drop a perpendicular. And sometimes that perpendicular will be outside the triangle. These things will also meet up in a center called an orthocenter. And that's what we know about them. We're running out of time just a tiny bit here. Just to kind of show real briefly, you drop it, I'm looking for perpendiculars, I'm looking for perpendiculars. There's your orthocenter. While I'm handing out the homework, see if you can fill this guy in. See if you can work out